Okay, I want to talk a little bit more about entropy. You've seen some introductory videos, the Sandcastle video, and the Hour of Time, and a basic introduction. I want to get into a little bit more depth with it for you here today, fill in some gaps. But don't think you're going to have to do the calculations that I'm going to show you. I just want to give you a fuller understanding. This is the equation for entropy. Entropy is S, and entropy is equal to K, which is a constant, called the Boltzmann constant, times the logarithm of capital W. Capital W is called the weight of the configuration, and it's a statistical measurement or variable. And so you can see here that because this is a constant, this is just a function, a log function, that entropy is really dependent on this statistical parameter here. Now let's get into a little bit of what W is. This is the equation for W right here from Wikipedia. W is equal to capital N exclamation point. Now that means factorial. Now that kind of a factorial is simply this. Let's say that n was 3, then n fac would be 3 times 2 times 1, or 6. Okay. If n was 4, then n fac would be 4 times 3 times 2 times 1, which is 24. Okay, so that's how factorials work. Now in this case, capital N is the total number of particles in the system. Remember the guy on the beach talking about the number of particles of sand. And then that's going to be divided by the product of the factorials of the populations of each energy state that is occupied in the system. Okay, so it's really about energy states. Let me show you what I mean here. I've set this up in a little spreadsheet, and W here, which is showing the answer 6, I've got the factorial equation in here that I just showed you. And right here I've got 3 different energy levels that are available to this system. Maybe this is an atom with electrons, and they can be at energy level 1, 2, or 3. And here's the particles. Now I have 3 particles in this system, and in this case I've put 1 particle in each energy level, or each energy state. And you can see that the weight of my configuration is 6. Now what this really is telling me is that there's 6 different ways that I can take 3 particles and put 1 in each energy level. For example, if I had particles and labeled them A, B, and C, then I could go A, B, and C, A, C, and B, and so on. And there's actually 6 ways for me to distribute them. Now, what if I change this configuration and make it like this? I'll put 0 in this state, 0 in this state, and I'll put all 3 in the first energy level. Let's see what happens to my W. It becomes 1. So there's only one way to put all 3 in the same energy level. That is, put all 3 in the same energy level. What if I put 0 in one energy level, and then 1 in another, and 2 in the last? What happens now? Well, it turns out there are 3 ways to do that. Okay. Now, since S equals K ln W, or K log W, we can see that the entropy will be highest in this case right here. And the next highest state, and entropy state, will be this, and the last will be this. All right. Now, the second law of thermodynamics would say that left to itself, and all other things being equal, a system like this would tend to evolve from this state to this state, and finally to this state, to maximize its entropy. All right. Now you can see obviously things would get much more complicated if I had a lot of particles. Let's just see what would happen. Let's just step this up a little bit and make this 10, 10, and 10. And you can see that entropy W climbs very rapidly in a case like this. It goes through the roof pretty crazily. Now just imagine if this, instead of 10 particles here, we had Avogadro's number, so we were talking about a mole. Imagine what would happen to our W value. So this just gives you a picture of a couple of things. One is, what is W? It has to do with the number of ways you can arrange the particles and still get the same kind of shape to your energy distribution. All right, because what we're talking about is the distribution of particles among the energy states. Now, let's go back to this just for a second here. When I have one in each, this right here is called a macro state. That is, there's one particle in each of 3 energy states. But if I was to say something like it's particle A here, particle B here, and particle C here, that would be a microstate. That is, a particular particle is here, a particular particle is here, a particular particle is here. It would be a different microstate if it was B, C, A, or something like that. But there's 6 different microstates that would make the same macrostate 1, 1, 1. Okay? So this is really what we're getting at. It's just kind of another layer down from the sandcastle. It's not really just about spatial distributions of particles. It's about their distribution among energy states. Okay, and the more kind of spread out the particles are through a broad range of energy states, the more we see a higher entropy. All right, if all the particles are in the same energy state, then that's a very low entropy system. Okay, now let's look at a real system and what it might look like. This is a little applet that allows me to make a whole bunch of particles as long as I make them a square. Alright, so I've got 144 particles in this case. Now in this picture here, in this little graph, what I've got on my y-axis is I have the energy. Okay, the energy of the particle. This is corresponding to my energy states on my little spreadsheet. Alright, and then going to the right here, this is, oh I'm sorry, I just misspoke there. On the y-axis is the number of particles, and on the x-axis, in this case, is the energy state or the energy level. So it's kind of turned from what I showed in the spreadsheet. But let's watch what happens. So if we start out with all of the particles, 100%, that's the red bar here, 100% are in this kind of intermediate energy state, this medium level energy state. And what happens if I click run here? They're just going to start to bounce around. Now what they're going to do is they'll be colliding with each other. And when they collide, they will exchange energy. So they all start holding the same amount of energy. And then as they collide, they're going to be exchanging energy randomly among each other. Some are going to lose energy in each collision. Some might gain it. In the next collision, they might lose and gain, and so on. Now, as you can see, as you might expect, what happens is the energy becomes randomly distributed among the particles, or the particles become randomly distributed among the various energy states. And it's very interesting that you can predict the shape of this distribution. You can see it almost has a bell curve sort of shape. And the blue line is what's called the Boltzmann distribution. That is the predicted distribution of particles among the energy states in the system. All right, and over time, the system moves toward that. Let's start it again. Let's watch it. We're going to make it go a little bit slower so we can see what's happening here. See that? We go to a more random distribution of particles amongst the energy states instead of them all having the same energy state. That's entropy. And why does it happen? Simply because there are more ways to get this than there are to get this. Okay? There's only one way to get this. You got to put all 144 particles in the same exact energy state. Give them all the same exact energy. There's only one way to do that. However, if we get to this, there are a huge number of ways to set the system up like this, with this number of particles in this state, 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 and so on. Now from a qualitative standpoint, you can kind of see the difference. Watch this. Highly ordered system, right? Now watch what happens to the orderliness of the system as I click run. It breaks down, and this is a much more disordered system. So you can look at it spatially too. How many ways can I arrange these particles and still have a picture that basically looks like this? Okay. Now, in contrast, how many ways can I arrange them and have a picture that looks like this, right? Now, let's see what happens as we increase the number of particles. Or as we decrease it. Let's decrease it and see what happens. Now, one of the things you'll see with this is that it doesn't really ever attain to that blue line, which is kind of the goal of the system, is to reach that Boltzmann distribution. It doesn't really get there because there's a large number of particles in it. It kind of approximates it, but it doesn't really get there. But if I have a lot of them, then what I get is a much smoother, nicer distribution. It approaches more closely to the ideal Boltzmann distribution. Alright. Now, as I showed you before, and this doesn't do the calculation of W for us, but as I raise the number of particles, entropy is actually going to be going up as I increase the number of particles. So if there are more particles in a system, entropy will go up because of W will go up, just like I showed you on the spreadsheet. Now let's see, the next thing I want to show you is kind of a general trend that we see in terms of entropy in a system. Now this chart shows two effects. As we raise the temperature of a system, the entropy in general goes up. And the reason is that we're putting more energy in it. Now when you put more energy in a system, there are going to be more, the particles in the system can attain to higher and higher and higher energy levels. So basically there's more and more options. So it's just like adding energy to a system would be like if I go in here and I say, oh, I'm going to start adding more energy levels. Okay? And that's going to make more and more options available. So I can keep adding energy levels here, and I can, because if I've got more energy in the system, then particles can be at higher and higher energy levels as well as still being at the lower energy levels. So that enables me to have a much higher entropy. I've got more boxes, as it were, to put my particles in. So as the energy level goes up, the number of energy states possible goes up. Now, the weird thing on here, though, is if you look at these breaks right here, what those are is the phase transitions. That's the transition here between solid and liquid. There's a big jump in entropy. And then between liquid and gas, there's another big jump in entropy. And you can look at that real qualitatively and say, and spatially, you can say, okay, a solid is very orderly, that makes sense. And a liquid is less orderly, it's more random. That's true. And a gas is even less orderly, it's much more random. And that works. So the idea of increasing disorder with increasing entropy kind of works for this whole thing. In fact, as you raise the temperature, they're going faster, and you can picture that as being more disorder, okay, more randomness, more chaos, as it were. But if you want to look at it in terms of energy levels, or interpret it in terms of energy levels, like I was just doing earlier, you can look at it like this. There are fewer energy levels available to a solid because particles in a solid have less freedom of motion. Basically, all they can do is vibrate. So all they have available to them is vibrational energies. Okay? But in a liquid, they can vibrate and they can do other things too. They can rotate. They can stretch their bonds, maybe, if they are, say, a water molecule. Water molecules can bend and so forth. They can rotate, they can slide around, so they can have some kinetic energy of motion as well as just vibrational energy. So there's a lot of different options. There's more options for their motion, and so there's more energy levels available, a lot more energy levels available. Then when we go to the gas, now they basically have total freedom of motion. So there's a lot of ways for them to have energy. They can have energy of straight line motion. They can be vibrating, rotating, stretching bonds, bending, all sorts of things, all sorts of ways they can have different amounts of energy in a gas. And that's why we see this huge jump. It's about freedom of motion. Okay, and so this is a great graph to remember in terms of when we try to predict what's the energy change of a certain process. Here we can predict the energy change when we're raising the temperature, the entropy change when we're raising the temperature, and the entropy change as we change phases. From solid to liquid, entropy goes up, and from liquid to gas, entropy goes up. All right. And I mentioned the other entropy change you'll want to keep in mind is if you're increasing the number of particles, you're going to raise the entropy. Now that's particularly important in some chemical reactions. For example, if I have a chemical reaction that actually increases the number of moles, so say I'm decomposing something, and it's going to produce 1 mole. I decompose 1. Here's a familiar example for you. This is hydrogen peroxide decomposing into water and oxygen, and you can see here we have 2 molecules decomposing into 3 molecules. So this would be one way we could increase the number of particles in a system, and we would expect W to go up because of that, because now we've got more particles to distribute among the energy levels, or among which to distribute the energy, if you want to say it that way. And we've got so we're going from 2 moles to 3 moles, for example. So increasing number of moles in a chemical reaction will mean greater entropy. Now there's even differences in entropy between particular molecules. For example, you could look at the entropy of an H2O2 molecule versus the entropy of an H2O molecule, and it's going to have to do with things like the bond strength and the shape of the molecule, the way that the bonds can bend, like how many different ways can it twist or bend, or how many different ways can you distribute energy around this molecule. So even different compounds will have different entropies. So the last thing I want to talk about with respect to entropy is the so-called second law of thermodynamics. And the second law says that basically the entropy of the universe tends to a maximum. Now in any particular process, the entropy of a system, a reaction system or an object or whatever, can either go up or down. And then it generally changes the entropy of its surroundings as well, however. And so if we look at the whole universe, the universe as a whole, in fact any isolated system, that is a system that can't exchange heat with its surroundings, if we look at the universe as a whole, then entropy always goes up in any spontaneous process, in any process that happens on its own. So this is how it's formulated here. The little d's are incremental changes. You can think of them as a little delta. So for any small change in entropy per small change in time, we've got a change in entropy of greater than or equal to 0 for the universe as a whole. Now the implications of this are that the entropy of the universe is always increasing and will continue to increase until it reaches some maximum, presumably. Now what that means is kind of like, I mean, that may be a little disconcerting to you, because you may be thinking about entropy as disorder and randomness, and you may think that the universe is becoming more and more random. Well, in general, you would be right. If you think about the universe right now, there's a fair amount of randomness to it, but there's also a lot of order, spiral galaxies and so forth, and there's a lot of concentrated energy. We're nowhere near the so-called heat death of the universe, the maximum entropy, when the entropy is distributed with the greatest weight of configuration. Now, when it does reach that point, the so-called heat death of the universe, it'll be basically just a vast thin soup of matter and energy, kind of nondescript, with nothing interesting happening anymore, and of course no life long before that. In terms of the heat death of the universe, is the Wikipedia article. Basically, you've got about 10 to the 100th years to reach that stage. And it says after that time the universe enters the so-called dark era and is expected to consist chiefly of a dilute gas of photons and leptons. And basically you're going to have very little happening after that. Now maybe you're worried about that. I don't know. Maybe it worries you that that's going to happen in this period of time. Of course, maybe something will change before then. If Ray Kurzweil is right, then artificial intelligence will take over and become more and more intelligent, and someday maybe be able to stop this process. If you're a religious person, you might think that God will stop this process and initiate some change before that time. But in any case, this is what the second law is pointing to, is this kind of maximum entropy of the system. And that is